recover the money. Okay, and the emission is better. Okay, to get the oil, right? Not just only the seed, but there are some parts of the trees, right? Those are waste or residue, right? This one, where you have a raw materials. This is tung oil. This is tung seed. This is palm seed. I think everyone get familiar with this one, right? This is tung, right? Okay. After you extract it, right? You get the oil, and oil can be used to produce biodiesel, right? And how about this one for the rest, right? The branch, leaf, right? You throw it away, right? And this one, normally, this is is also waste, right, or residue, and also glycerin. Those are waste. So you have to manage it, right, to get the zero waste. Because if you throw it away, right, it will pollute to the environment, and some part could be generated value added, and you can reuse it. Okay, these are the residues from a tung plant, right? We have branches, shell, and seed cake, right? And you can imagine, you can see the number per rye. Okay, I try to remind you, 1 rye equals 1,600 square meter. Okay, and this one you can see that you have some residues around 2,000, nearly 3,000 kilograms per rye, right? And I think the amount is quite high. So we have to think how to reuse it, or to recycle it, or to generate the value added. But because I'm in charge on the energy, therefore we try to transform everything to be energy. Okay. Now look at the concept of zero waste management, right? Zero waste, right? Just right, promote not only to reuse and recycling, but more importantly, it promotes prevention and product design, right? Okay, it means that, okay, if you can recover everything back, no waste to the environment, it's good. And also when you recover everything back, it means that you can reduce the raw materials. When you reduce the raw materials, it means you can reserve the resources, okay, for the next generation, okay? And again, you have to be aware that if you would like to regenerate it back or generate the value added, you have to select the suitable or appropriate technologies that consume very small energy input. Otherwise, the energy input is too high, right, compared to the output. You have to take care about that one too. Okay, and again, if you can generate something about the zero waste, then this one also, the zero waste, right, strongly supports sustainability, right, by protecting the environment, reducing costs, and the resources. Okay, that's why Chiang Mai University also interested about this one. Okay, the concept of zero waste, right? You generate materials, energy, something like that, and also you have some waste, right? But if you get the final zero waste, right? Nothing, just only in, nothing out. I mean, in terms of waste. And again, you can reduce the raw materials, and also you can reduce the any input. Okay. Okay, let's go back to our tung oil plant, right? Again, since all the waste, right, we try to convert back into energy. For example, the leaf and the branches of the tung oil, right, will transform into RDF5. RDF is the word comes from refuse-derived fuel. It means that you take all the residues, right, shred into small pieces, dry it, then and you press briquetting, right? As then you can get a stick of the fuel. Okay, and for the oil, right? You have the glycerin. Then, in our experience, we found that glycerin can be blended with the RDF. Glycerin can be taken as a binder, right? Then you can form the stick very well, the nice stick. And also RDF, after blending with glycerin, we found that the heating value is higher because glycerin actually is a part of oil, right? And normally you dump it out, right? But if you blend it, you can increase the heating value of the RDF. And RDF can be taken as a feedstock in the gasification. Gasification is a process, combustion process that the oxygen amount is not high enough. Therefore, the output is CO and hydrogen and carbon monoxide. And those one can be used as a fuel and run. You can take it, and that one is called syngas, and this one you can run the engine for power generation. Okay, and for the oil, right, you can generate biodiesel, and the seed cake after the oil extraction, right, will be taken into a process of pyrolysis. Pyrolysis is a combustion process that there's no oxygen inside. And the output of the pyrolysis is a biochar and bio-oil. Biochar and bio-oil, okay? And for the pyrolysis, there are two techniques, slow and fast pyrolysis. It depends that what are the products you need. If you need more more char, more biochar, right? You can take the slow pyrolysis. And if you need more oil, you use the fast pyrolysis. Okay? You can get bio-oil and biochar. Okay, then you can see that all the waste, right, can be used. Even in the gasification, if you have the ash can be blended with mortar, cement mortar, right? And you can generate a concrete. I mean, low quality concrete, right? Therefore, you have to think about the technique that how to use the materials, use the waste, and try to find out the appropriate techniques that consume very few energy input. Okay. And then the concept of this one is. Of course, that is not absolute zero. It will be near zero waste or something like that. Okay. And anyway, because we are in engineering, we have to find out the techniques that simple and also consume very low energy. Otherwise, you know, if you still use more energy input, right? So you have to judge. Anyway, we have a technique to judge that which technology is the most appropriate. In our lab, in our university, we have a technique of LCA, life cycle assessment. Therefore, life cycle assessment will judge that this one, which one is more friendly to the environment. Okay. So let's go to the details. Okay. This is the properties of the tung oil, right? This is a seed cake after extrusion, right? You can see the heating value is not high, it's very low, right? For the normal fuel such as diesel, the heating value is around 42 or 43 megajoule per kilogram, but for this one it's around 14, right? Small sulfur, right? Okay, you can compare with the palm, okay? Okay, now the seed cake, right? Looking for the slow pyrolysis. Okay. Slow pyrolysis is mean that the heat input is very slow, not so high. Around this one we keep the temperature around 300 to 500 degrees Celsius, 300 to 5 degrees Celsius, 500 degrees Celsius. I think someone thinking that, okay, when you need very high temperature, something like this, how much any input you have to supply into that one. Okay, anyway, you can get the oil, right, at different temperatures. If you generate temperature very low, there's another word, it's called torrefaction. Torrefaction, right, around 300 degrees Celsius is a term of pyrolysis. But for torrefaction, you get a very high amount of char, biochar. Right? For very high temperature, is if you have more complete pyrolysis, right, you will have more oil and less amount of char. Okay, and you can see the color. Okay, and in our lab, we found that for 1 hour should be long enough. Okay. Of course, this one we have a furnace, right? And in the lab scale, we use electrical heater. But right now, we develop another kind of furnace, right? And that one uses gas. Okay. But in this one, we use the electrical heater. Okay. And we can maintain the temperature around 300 to 500 degrees Celsius. There is one technique, a simple technique to maintain the temperature. You can use storage. In our lab, we use the ceramic ball, right? Because we are close to Lampang province. Lampang is very famous about the ceramic, right? And a lot of cheap ceramic balls. And ceramic ball, right? You can use it as a storage. Then you can maintain the temperature, right, to be uniform for the whole furnace. Okay, and this one we can produce. Bio oil and biochar. This is biochar. This is biochar from Tung seed cake. This one very low temperature, 400, 500, and 600. You can see the color for the biochar. Right. This one, after we extrude the seed, we found that some oil still inside. Right. Therefore, you can see that you can see the color of oil, right? Because the oil does not flee away. I mean, completely. But for higher temperature, right, the color is changed. Okay. And this one, the heating value is quite high because some oil is still inside. Okay. But this one is not so good because, you know, it's very sticky because of still you have oil inside. Very difficult, I mean, after the process, right? Very difficult to take it out because it's very sticky. But for this one, no problem. Okay. Anyway, now I think someone will thinking, you produce biochar for what? Right. Right. Actually, biochar, right, this one has a very high content of carbon. This is a technique we call carbon sequestration. Okay, it means that you can transform the carbon in the atmosphere because carbon dioxide, right? Carbon dioxide is absorbed by tree under I forget the photosynthesis. Yeah, something like that, right? Okay, right? It means that you absorb CO2 in atmosphere and transform it to carbon or biochar, and this one can be as a fuel for the next generation. Okay, you can burn it. This one, and for agriculture, right? This one can be used to improve the soil quality because of the high porosity of the carbon, and this one carbon is very strong. The structure is very strong, and then with a good porosity, right? You can this one can absorb the nitrogen or the fertility inside, right? Okay. Okay, and you can see the heating value. At a low temperature, right, 400 degrees Celsius, the heating value is around 35%. And for 5 or higher temperature, heating value is less because the oil, right, is going out, right? And you can get more oil. And you can see the composition, oops, sorry. The composition, right? At low temperature, you can get more amount of biochar. But for high temperature, you can get more amount of bio-oil, okay? And for the bio-oil, the quality is not too bad. You can use it to replace the heavy oil, right? You can run it in the boiler, right? The heating value, I'm not quite sure that I have it or not. Oh, the heating value, you see, is around 33 compared to the diesel or heavy oil. Heavy oil heating value is around over 40 megajoule. This one is around 30, right? But then, and you can take it as a fuel in the burner. One main problem of the bio-oil that the smell very strong, right? And one more problem is about the stability, because in the bio-oil you have a lot of oxygen. Then if you would like to use it as a real fuel, you have to expel oxygen. In our lab, we preparing a technique. We use ultrasonic to check it and expel it. This is we are preparing to do this kind of lab. Okay, and again, since the quality is not so good, therefore you need a process of refinery. And anyway, you have to be careful, because when you refine it, it means that you have to put some materials such as catalyst, yeah, right, and also some energy. So you have to think about that one, right? If you would like to refine it, it means that you have to put some more energy input and some more materials, and you can get zero waste or not. You have to take care about that one. I think the bio-oil refinery now is a big topic for the Thai universities, because we try to transform the bio-oil into biogasoline, right? And also bio-kerosene. Because now we have a big problem for the air transportation, right? If you use fossil kerosene, probably we can't fly over Western country, because we have to pay a big charge, right? Therefore, now the NRCT, National Research Council of Thailand, right, plan to give a funding on the bio-kerosene. I think for the Thai researcher, I think you have to think about that one for the bio-kerosene. What will be the good catalyst? What is the appropriate process to improve the quality of oil to be bio-kerosene, to upgrade the oil? You have to think about that one. Okay, and another one is the fast pyrolysis. The previous one is a slow. For fast pyrolysis, it means that you have to generate temperature very fast. The rate of the heating rate is around 500 degrees Celsius per second. It sounds to be very fast, right? But very easy, right? Most of the university, the reactor, they use the fluidized bed, okay? But for us, because our background is a mechanical engineering, we use a free fall, right? And use a storage. It means that we maintain the temperature to be around 500 degrees Celsius, and then you can feed the powder of the biomass, right? Then you can get 5 degrees Celsius or 1,000 degrees Celsius immediately, and you can get bio-oil and biochar under pyrolysis. Okay. You can see that we feed everything under the nitrogen, right? Everything is done under the nitrogen atmosphere. And for nitrogen, very easy to get it, right? You can suck the air through an absorber that absorbs oxygen, then you can get nitrogen, right? In the what do you call the gas station, right? When you refill the tire, right? So in some gas station, right? That refill the tire by nitrogen. Okay, the same technique. Okay, Okay, that one right now the nitrogen is not so expensive ratio because you can get it from the air, right? Okay, and for the fast pyrolysis, the main products is bio oil, and the biochar is not so good. The quality of the biochar under the fast is poorer. I mean, for the biochar, the quality of the char is poorer than the fast pyrolysis, but you can get a high amount of bio oil. This one is around 5 degrees Celsius. Okay, you can see that under fast pyrolysis, right? You can get oil around 70%, high amount of oil, okay, and a low amount of biochar. And you have some gas going outside, and gas, this one can be recovered as a fuel to heat the reactor up to 500 degrees Celsius. Therefore, for this one, nothing coming out. Everything is used. Okay, for this. Okay, as I mentioned, when you get the bio oil, right, you have to refine it. There are many processes. I think some university has this kind of technology, but everything is done in lab scale, and everywhere you can see that they consume a lot of energy and put a lot of catalysts. You have to think about that one, how to do that, and it is a good research topic in the near future. Okay, now for that is a part of the bio oil and biochar. Now look at the RDF. This is our RDF. Could you remember that the branch, the leaf, after we dry it and shred it into small pieces, then we compress it, and this one is called RDF5. RDF5, right? RDF actually is classified into 7 classes, right? And for this one we call RDF5. And again, for this one we blend glycerol. After we do we generate the biodiesel, right? We have glycerol as a byproduct, and that one also taken as a binder, right? And we can get a good stick, something like this. And okay, this one will be the feedstock as a fuel to run the gasifier. And the gasifier generates the syngas, and syngas is used to run the engine for power generation. Okay, and this is the model at Metro University, our partner. Then for us, we just produce just only this one, right, and send to another partner, right, because we have no space to generate a big power plant, something like this. And Metro, in Metro, they try to claim himself that Metro try to claim herself, right? That try to use the renewable energy for power generation. Okay, and so Metro University is our client, right? Then we support this one. Okay, and this one. You can generate electrical power, right? And the ash, right? It can be taken, can be used to and blend with the cement, right? For in construction process. Okay, and again. One thing you have to be careful that when you use biomass as a fuel, there are some particulate matters going out. And a lot of people say that you can use electrostatic precipitator to hold the particles. But in the real practice, there are very small in terms of submicron particles. And for submicron particles, the normal ESP could not hold that one. Right? Submicron particles, the size is very small. Therefore, right, you're going out. When it's going out, right, you breathe in, right, it go to your lung directly. then you have to find out the technique to protect that one. And we found this one is our development. This one we call agglomerator. Again, we generate plasma. Our concept, right? If we cannot, for small size, we cannot hold it, then we have to generate or agglomerate it to be a bigger size. How and how to agglomerate it? Then we generate plasma, and when we inject plasma into the vicinity of air, right? You can ionize the air into positive and negative, and then when small particle passing through the plasma field, for example, from the left-hand side, you see nothing, and you think that the air is really clean. Actually, there are a lot of small or submicron particles. Okay, when the particles passing through the plasma field, this is plasma field, right? In the dark, you can see the color, but for this one, you cannot see the color. Then when the small particle or refined particle passing through the plasma field, right? They are charged with different polarities. And when they have different polarities, positive and negative, then they agglomerate, and you can see them. Okay. Again, right now in Thailand, there are a lot of biomass power plants, right? And when you go there, you see very clean. But when you go closely and you feel that your eyes are irritated, it means that there are very small particles. I used to visit many biomass power plants. You know, I have to take the glasses, good glasses, and also visit the eye. To wash my eyes, right? To protect that one. That one is very dangerous, you know, because it's very small. You can't clean it clearly. It stick into your skin, your eye skin. Very dangerous. You have to be careful if you go to, and if you have a chance to visit those kind of power plant. You have to be careful of that one. Okay, for this one, right, you can see that we can accumulate to have a bigger size, and the ESP can hold this. Okay. This is very simple, very easy. And to generate plasma, we use a non-thermal plasma. Therefore, we consume very few power. And of course, the design of the electrodes, this one is quite confidential. This one we have patented it. Okay, and you can see the results. This one give an example. We generate the pulse plasma at a voltage of 35 kilovolt, and the frequency is 10 kilohertz. And these are the distribution of the small particle, of the very fine particles, right? This one is a range of 0.3 to 0.5 micron, and this one is over 5 microns. Okay. After this one pass our agglomerator, right? We can reduce. You see, for the low speed, this one is 0.5 meter per second. We can reduce the small particles around 94%. For normal ESP, this one will pass the ESP. I mean, the ESP cannot hold this one. Okay. And again, you can see that the number of 5 micron particles increase. It means that the small number particles, right, agglomerated to have a bigger size. Then you can get more amount of the bigger particles. Anyway, when you have when the speed is higher, the efficiency drops down, right? Therefore, you have to think how to control this one. Anyway, we have another student, right? We put a bluff body to generate a shedding. I mean, after the flow passing to a bluff body, that one will taken as a vortex generator, and there is a shedding. Therefore, when it's a shedding of the airflow, it means that the particles has more time or more distance to stay in the plasma field, and we found that the performance is better. Okay. And again, when you get this one, right, it means that you protect the emission to the environment. And sometimes you have some more particles, some more carbons, right? Okay, after you, you off the machine, right? You can get the particles, and then you have to think that how to take that one back, right? Don't leave to the environment. You have to think about that one. Okay, and anyway, you can see that actually there are many techniques, right, to protect or to prevent, right, the emission or something like that. Or there are many processes to upgrade the oil, but you have to be aware that each technology consumes energy input. Then you have to find out which one is the most appropriate, right? And which one give a very low energy input. And actually, which one is the most simple, because this one you have to implement to the public, right? If the process is very complicated, no one can use it. You have to think about that one, right? This one just give you an idea, right? That what we have done right now in our university, right? This one just only the one example. Actually, we have the other processes. If you have time, I think I would like to invite you to visit our Chiang Mai University, right, to see what the technologies we have, right, and which one that could be implemented. And some technologies right now still used in our university as the example. Therefore, when the visitor comes, okay, even the university still use it, right? Okay, it's possible to be implemented. Okay. So I say that the awareness on energy efficiency and environmental impacts are very important. You have to take care about that one. Okay. Not just only the cost or something. The awareness is the first step, right? Okay. I would like to thank the National Research Council of Thailand. We have a Sino-Thai project, because when we are talking about the biofuels, of course, we have China, right? It's very close to us, and China is very advanced about the biomass energy, right? In Thailand, right, we have a small scale. Now we need the technology, right? How to enlarge the scale to be commercial scale or something like that. Okay, and also I would like to thank the Office of Higher Education, right, under the National Research University project. As you know, that Chiang Mai also one of the research university in Thailand, right? Okay, and School of Renewable Energy, Metro University. This is our partner, right? That right now in Chiang Mai, right, we have a many university, and we try to generate a cluster to work together. Okay, and again we have a partner from Mahasarakham University. Then we would like to, not just only thinking about the northern part of Thailand, we also thinking about the other part, right? And also if RMUTP, right, would like to join with us, I think we are very welcome. Okay. And lastly, we thank Faculty of Engineering, Chiang Mai University, right, for offering the space and some part of the money and the students, right, and the RNTA to work with us. Okay, thank you very much for your kind attention. Okay, thank you.
Thank you for Professor Paul. Any question? Any question?
Why is it not possible to use just cracking towers like you use for usual oil?
Cracking tower?
Yeah, the cracking towers are used in refineries. Where you have
in our lab, we use another one we call free fall. I'm not sure that similar to yours or not. That we have a column, right, a tower, right, and we can feed we feed the feedstock right through that one, and under the atmosphere of nitrogen. Right. I think
oil industry, in refineries, you have that you separate a different chain length of polymers by having different stages, and you can get the kerosene.
Sure. That is a fractional column, right? right? But for the bio oil, it's not quite easy because you have to expel oxygen first, right? And for fractional column, right? You need different temperature, right, for the condensing, right? Not quite easy, not quite easy, because you can ask that the Amini University try to use that one, because for fractional column, right? Sometimes you can't separate completely, right? You need a catalyst or some absorber to absorb it, yeah. And the cost is very expensive because you know, if you use the absorber, right, when it's saturated. How to do that? How to regenerate? When you regenerate it, you consume a lot of power, right? Or you throw it away. Oh, that is not zero waste, right? Not quite easy. It sounds to be easy, but in practice, no. You know, because we try. You know. When we finish the project, right? We have to think that if we would like to implement this one in the community. How about the people in the community, how to use it? We have to think about it one.
Excuse me, I'm not type of engineering, I'm in microbiology. I just wonder whether this one can be applied used with microbial.
Okay, actually my lab, we also take microalgae, right, as a source of the biodiesel. We do that.
Bacteria or some fungi.
Yeah, but in our lab we use chlorella
Algae.
SPP, yeah, algae.
But algae take time and needs a photosynthesis.
Yes.
And also a lot of
we how to say, we culture it, right? Cultivate it, right? In a vertical column, our design. Actually, we are not the people in the microbiology, right? But we in Chiang Mai University, our lab also is a big group on the solar thermal energy. Therefore, we design this one in a vertical reactor, right? And the algae absorb CO2 in the atmosphere, and we cultivate it around 20 days. Then we harvest it, dry it, okay, and paralyze it, because for chlorella the amount of oil is not so high. It's around 14%. In our lab, 14. In the other labs, 40. 40, but not chlorella, not chlorella another type. But for us, we use chlorella because chlorella can stand the open environment. Okay, very easy, right? And under pyrolysis, we can get the oil and also biochar without any problem. But the cost, we found the cost is very expensive. The cost, 1 liter of oil, I think the cost is more than 10,000 baht. The cost, because you see, it seems that everyone say that microalgae will be the 3rd generation for biodiesel or something like that. But we found that the yield is not so high. I mean, to generate that one. Even we use solar energy, you see, right? Not quite easy. We do it. We do it.
But I heard right now it has some engineered bacteria like E. coli they had done, and they said that one can generate oil. Yeah,
that one they don't use this kind. They don't use pyrolysis. They extract it, extract, compress, because the oil inside is quite high, right? But you have to think about the most expensive is about the nutrient, the food, for the nutrient of the algae is very expensive. And then when you get that one, right, when you get the algae from how to say, I mean, from the solution, right, then inside is still some nutrient. How could you control the nutrient? And the cost of the nutrient is very expensive.
It has many ways.
Yeah. And right now, some group in our Chiang Mai University, they try to extract the algae in the solution by using electric field. They charge it, right, and then accumulate it, and then they can get algae easily. Otherwise, we have to keep it, right, for I think for a long period, right, and make it, I don't know how to say, look like a deposit of that one naturally. Yeah, and you have to spend a lot of time. Then they use electric field to charge it. Because I'm engineer, right? Mechanical engineering, right? In mechanical engineering, not microbiology, so sometimes it's very difficult. Anyway, but we have talked with the School of Microbiology that when we cultivate it, right, harvest it, then the algae will be extracted. I mean, to get the carotenoid or something like that, right? And the rest, okay, sent to us to generate the waste, right? To generate the fuel. But you know, the cost for pharmaceutical and for food, right, is very expensive. Then this one can compensate the cost of everything. We think that right now to generate oil from microalgae, 100% is not so good. But if you extract something, right, yeah, that one is very expensive, right? This one can compensate, and the residue, okay, sent to us, okay, for because I just say that, okay, if you have waste or residues, okay, send to us. We can transform everything to energy, okay.
Yes, I wonder if you have considered economic impact of this zero waste concept. My question is that if this zero waste concept you mentioned economically feasible, I mean, yeah, you have to put a lot of energy into, you know, making or changing things. I mean, I wonder if in economics.
That's right, because you know, because when we put some technologies, right, it means that you have to put some energy, not energy, even the equipment, right, very expensive. Yeah. So a lot of people say that, okay, you can produce something very cheap, but the cost of the equipment is not included, because you get it free, right? You can get from the tax of the people, right? But and that one scale is too small. Then you have to think that if you would like to produce a prototype, you have to produce a prototype. Then you can clarify the real cost. Otherwise, no, very difficult. And again, you know, as I mentioned, you put energy, the equipment, right? More luxurious process. It's been very high, very expensive equipment. And how could you add up into your cost? Anyway, you have to be careful. Even the process, right? Right now we use the LCA to judge that it's good for the environment or not. And also studying about the energy efficiency, that the output energy is higher than the input or not. Right? If the output is less than the input, we do it forward.
What is the current production of the tongue bean as far as the farmers are concerned, and would there be enough incentive for them to produce it for oil production?
For the farmer, I think our concept right now, such as the plasma to generate the biodiesel, is very cheap. Okay, show you. Okay, this one. This one is nothing, just the electrode, right? And the white electrode outside just aluminum foil, very cheap. I think the cost is in terms of 1,000 baht. This one, the cost, the most expensive is about the variac, right? And the other part is very cheap. If we fix up the voltage, therefore in the real practice, no need to use the variac. We fix the voltage. Therefore, the cost is in terms of 40 or 50 US dollars, very cheap, and the farmer can produce it by himself because this is aluminum foil, the coil. Right. Just if the farmer, the community has their own plantation, right? They can extract the oil by themselves. Therefore, everything is the input from inside the farmer. And for the but for this one, it's rather expensive. For the ultrasonic is rather expensive. Okay, but anyway, the farmer can blend the oil directly without water, and you can use it to run their own engine. And this year we are preparing the bio lubrication oil because we can blend the crude vegetable oil into the lubrication oil, and we found that the property is very close to the pure lubrication oil, right? And the cost is very cheap, and then the farmer can use this kind of oil to maintain the equipment easily. Therefore, we are also always thinking about that one, because how to implement in the real practice, and everything must be simple to the people in the community. Yeah. We are always thinking about that. Just the people come to our lab to be trained, just 2 or 3 hours. Okay, use it, and that's all. And we don't want to change the lifestyle of the people. Just add up something more, a little bit. Yeah. Yeah. We are aware about that one.
Any question?
This one.
Just one question. How does the tongue oil compare to other oils like palm oil or sunflower oil?
Sunflower oil is for food, right? Yeah. Palm oil right now is also for food. Okay, but for tung oil, it's not. You cannot eat it. You cannot eat it. Okay, this is the main the main advantage. But there's another drawback. This one is used in industry, in in painting factory, right? Therefore, the cost. The factory perhaps give more money about that one. Anyway, you have to make the allocation. The management must be very good, and depends on the policy of the government. But you cannot eat it.
Any question?
You also mentioned the possibility of using it in jet fuel. Have you done any testing in the jet fuel for aircraft engines or something similar?
We have no lab about this one, I think. But I've heard that next year, right, NRCT will funding this kind of research project. So we need the partner from. If you have the expert about this one, I think it's pretty good to I think come to assist and work with us. Because as I know that to upgrade the oil is costly. Right. Yeah, so we have to find out how to do that. In the lab, frankly speaking, in our lab, we used to inject plasma into the oil, and just only once, we found something coming out, and we found that the smell looked like a kerosene. But we can do it just only once by accident. But until now, we cannot do it again. We don't know why. And how? Yeah, because now we try to find out the people who has a knowledge and know-how on catalysts to work with us. I think if your colleagues, we would like to do that.
Any question? Thank you for Professor. We hope that his research help you in the future. Thank you, Professor.
Okay, thank you very much.
We have one keynote speaker after lunch, and now you can let's join lunch together.
Wow, I saw this. This is good. This is neat. Let's see what he's going to say. I'm very curious.
You will Here.
อะไรนะฮะก็ไม่เป็นความลับเนี่ยใครอยากดูก็ดูเขาไม่รู้เรื่องไม่ค่อยรู้เรื่องฮะก็คือเรามีเด็กปริญญาโททำก็ถ้ามาจากของเราจะเลือกโปรเจกต์ให้ตรงกับสาขาเขาเรามีเด็กไมโครไบโอโลจีมาเรียนกับเราว่ายังไงวะเป็นเมดไวส์เลยพอเราดู process เขายังไงไม่ถนัดถ้าไม่มีเมาส์ของเราเนี่ยจะมีหลายโปรเจกต์ก็คือเรามีนี่ด้วยนะฮะ Solar Detox ก็เราโค้ดด้วยไทเทเนียมไดออกไซด์ก็กำจัดพวกสารพิษได้ใช่ไหมในแสงที่มีอัลตราไวโอเลตอยู่ใช่ไหมแล้วตอนนี้เรายังไม่ให้กำจัดน็อกซ์เราก็ทำกำจัดน็อกซ์ก็เราโค้ดไทเทเนียมไดออกไซด์ใช่ไหมครับลงบนโพลีคาร์บอเนตแล้วก็ฟีดอากาศที่มีน็อกซ์เข้ามาเยอะๆแล้วเราก็เปลี่ยนน็อกซ์ที่อันตรายให้เป็นน็อกซ์ที่ปลอดภัยผมไม่รู้ตัวไหนต้องเรียนผมก็ไม่รู้ผมไม่รู้จักว่าน็อกซ์ส่วนไหนปลอดภัยไหมมันมี NO2 NO อะไรเนี่ยผมก็ไม่รู้ว่าผมไม่รู้ว่าคือเบิร์นเด็กเคมีมาทำไงก็เลยก็ทำนั้นครับซีโร่คืออะไรไม่รู้ต้องนั่งคิดนั่นเป็นโซลูชันเอทานอลใช่ไหมเราไม่ได้ทำนั่นกลุ่มอีกกลุ่มหนึ่งก็ทำของเราเป็นเพิ่มความเข้มข้นเอทานอลก็ฮีทเอาแต่ว่ามันมีทั้งฮีทแล้วก็ผ่านแอสซอร์ปชันก็ผ่านซิลไลท์นะฮะซิลไลท์มันก็ดูดน้ำดีดขึ้นมาเลยนะเพราะมันเลยอะซูโทรปิกได้เลยดีเลยง่ายๆซิลไลท์ในอุตสาหกรรมมีขายราคาถูกๆเยอะไปแล้วก็หาทางรีเจเนเรตมันกลับแต่ว่าใช้ได้กี่ครั้งก็ต้องมานั่งเช็คว่ามันจะรีเจเนเรตได้กี่ครั้งรีเจเนเรตด้วยที่อะไรก็มีทั้งฮีตติ้งใช้อัลตราโซนิกอะไรนี่ก็แปลว่าเราทำหลายเรื่องไงฮะมันก็เลยนี่ฮะนำบัตรหมดพอดีนี่ฮะคือเนี่ยเห็นไหมฮะแต่ว่านี่ตัวอย่างนี่เราโชว์พวกสลายเกลียวทองเนาะแต่ว่าคอเรล่าเราก็ทำอย่างนั้นเนี่ยเลี้ยงแนวตั้งเนี่ยฟีดคาลิบเนตโพลีคาร์บอเนตเบาๆกระจกแตกโพลีคาร์บอเนตมันเป็นแบบนี้ไอ้สกายไลท์อะไรนะมีราคาถูก2 แผ่นที่ประกอบกันแล้วปล่อย2 ข้างใช่แค่เราก็ทำไอ้ที่ตัวไฟยึดอยู่ในกันไม่ใช่ที่มันเลี้ยงก็20 วัน21 วันขนาดเลี้ยงงงๆไม่สวนเลี้ยงนะใช่ป่ะไม่ใช่ผู้ชีพเขาเด็กไปหาสูตรมาคือถามจากพวกไมโครไบโอโลจีอ่ะสูตรอะไรก็ผมรู้ว่าจริงๆแบบให้มันโตเร็วก็มีให้โตแล้วมีน้ำมันเยอะก็มีที่เราผมก็รู้สูตรไหนเด็กมีปัญหาเด็กเขาอยู่ไมโครไม่ถามอาจารย์แล้วว่าเด็กก็เติมมาแล้วคราวนี้เนี่ยผมจะปัญหาคือพอมันครบแล้วเนี่ยก็จะทำแบบก็ต้องทิ้งเลยแต่ว่าที่นี่ต้องมีสารทำยังไงแล้วไม่มียาเช็ค ได้ครับได้ครับได้ครับ
ถ้ามีโปรดักต์มีใบโปรดักต์อะไรแล้วเดี๋ยว
เนี่ยทำได้หมดนะฮะทำ pyrolyze ได้หมดนะฮะอะไรที่เป็นไฮโดรคาร์บอนทำได้หมดอะไรที่เป็นไฮโดรคาร์บอนเนี่ยทำได้หมด
พวกเปลือกผลไม้
ได้หมดอะแต่ว่าปัญหาคือต้องบดละเอียด
ต้องบดเดือดผงก่อน
ต้องตากแห้งแล้วบดเป็นผง
แต่ก็อันเราก็คงต้องเลือกอันที่มันมีน้ำมันมันจะเป็นคาร์บอนที่
ใช่ใช่ใช่ง่ายกว่า
แล้วปาล์มนี่ไม่รู้ลำต้นใบเบยไม่ค่อยมีน้ำมัน
ไม่ดีฮะเอามาอัดเป็นแท่งอย่างนี้ดีกว่าเนี่ยปาล์มอัดเป็น RDF ดีกว่า
แล้วอันนี้ไปเผาอย่างเดียวเพื่อให้เป็นแก๊สอย่างเดียวให้พลังงานสูง
ก็ถ้าเป็นพวกนั้นเนี่ยเผาโดยตรงได้ชาวบ้านก็ไปเผาโดยตรงได้พลังงานก็สูงแต่อันนี้ของเราใส่พลาสติกเข้าไปเพราะพลาสติกเป็นปัญหาขยะถ้าพลาสติกเนี่ยจะเผาโดยตรงไม่ได้ต้องไปเผาผ่านกระบวนการ
ที่ทานเมื่อวานก็เป็นขวด
ใช่ใช่
แล้วแคโรซีน
เคโรซีนคือน้ำมันก๊าซ
อาจารย์พูดบอกว่าเขาห้ามเดินทางเพราะว่ากลัวมันไวไฟ
ไม่ใช่ครับเพราะว่ามันเป็นฟอสซิลไงคราวนี้ก็คือเคโรซีนที่เราใช้ปัจจุบันเนี่ยนะฮะมันมาจากเชื้อปิโตรเลียมใช่ไหมฮะเป็นปิโตรเคโรซีนเพราะฉะนั้นเนี่ยเขาถือว่าไม่เป็นมิตรสิ่งแวดล้อมเขาก็จะชาร์จแพงตอนนี้ผ่านน่านฟ้ายุโรปผ่านน่านฟ้าญี่ปุ่นเนี่ยไม่ได้นะชาร์จแพงผ่านได้แต่จ่ายแพงเขาก็เลยจะออกกฎหมายเป็นไบโอเคโรซีน
แต่เราไม่ต้องใช้น้ำมันก๊าซเรามีอะไรทดแทนใช่ไหม
เจ็ตออยล์คือเคโรซีนคือเจ็ตออยล์ก็เคโรซีนที่คุณภาพดีขึ้นหน่อยนะก็คือเจ็ตออยล์
พูดท่านอาจารย์มีออกมาด้วย
เจ็ตออยล์เราทำไม่ได้ฮะต้องเพราะผมมชไม่มีพวก catalyst engineering ที่ทำได้ก็เป็นพวกกลุ่มจุฬากลุ่มขอนแก่นที่ก็มีพวก catalyst engineering ใช่ใช่เคมีวิศวะเคมีอุตสาหกรรมอะไรอย่างเงี้ยทำพวก catalyst ใช่ใช่ปิโตใช่โอเคนะฮะก็ถ้ามีอะไรก็ร่วมกันก็ได้นะครับผมเนี่ยเราทำพวกไบโอมีเทนด้วยนะฮะ
กำลังจะให้ชุมชนที่วัดหนองเสือแล้วผมก็เนี่ยราคาไบโอเค
เวลแกสจะมีกลุ่มหนึ่งศูนย์วิจัยนครพิงค์นั่นเขาทำระดับประเทศเลยครับระดับโลกด้วยนะผมว่าได้ฮะผ่านเราก็ได้ศูนย์วิจัยนครพิงค์ก็ทำเวลแกส
คือว่าจะเขียนโปรเจกต์เพื่อให้ชุมชนได้ไปทำบ้านของเขาอะค่ะ
ทางนู้นเขาจะมีโปรเจกต์ยักษ์เลยฮะเขาท
น้อยให้ชาวบ้านทำเอง
ำก็ลองคุยเขาดู
ที่ไหนนะคะนครพิงค์
มาที่เชียงใหม่ฮะอยู่ในเชียงใหม่
กลับวันไหนอะคะ
เดี๋ยวก็จะขับ ครับเพราะว่าเย็นนี้มีพายุจะเข้าฮะเลยกลับวันเชียงใหม่
ไปที่เชียงใหม่
จะมีพายุเข้าไงฮะก็วันนี้จะเข้า
ทำไมอะคะเขามีพายุ
ผมอยู่เชียงใหม่ไม่กลับ
รีบกลับไปก็เจอพอดี
ก็ต้องรีบกลับก่อน
กลับไปดูแลค่ะใช่ไหม
เรากลับไปก่อนนี่ฮะนี่ก็
งั้น
นี่
ขอเบอร์โทรอาจารย์
ได้ครับก็ขออาจารย์081ครับผมนำบัตรผมหมดแล้ว081ครับ950 8630ธนงเกียรตินะครับอันนี้ก็เราก็กำจัด NOx นะฮะแล้วเราโค้ดเรามีแผ่นที่โค้ดด้วยไทเทเนียมไดออกไซด์เราก็พบว่ามันเปลี่ยนจาก NOx อีกตัวหนึงเป็น NOx ตัวที่ปลอดภัยกว่า ผมก็รู้มันตัวไหน
NO2 ไม่ใช่ NO2 ก็ยังเป็นพิษ
ใช่ไม่ใช่ฮะกำจัด NO2 คือถ้าให้ NO2 มันเพิ่มขึ้น
ให้ NO2 เพิ่ม
หรือลดลง
ลดลงนะคะอาจารย์ต้องลดลง NO2 นี่เป็นพิษใน N เฉยๆหรือเปล่าคะ N เฉยๆ
ไม่รู้ตัวไหนอะ
เดี๋ยวไปหามาเดี๋ยวบอกอาจารย์
คือ
เฮ้ยเด็กมันตอบอะคะ
เด็กเขาเทสมาแล้ว
งั้นเด็กต้องรู้มากที่สุด
ใช่ก็ไม่รู้
ค่ะเด็กต้องรู้มากที่สุด
มันมีหลายตัวซึ่งผมไม่รู้ตัวไหนเป็นพิษ
แต่รู้ว่าออกซิเจนน้อยลงยิ่งน้อยยิ่งดี
ไม่รู้ฮะ
ยิ่งเป็น N เฉยๆยิ่งดี
ครับ
N2 เฉยๆ
ก็คือหน้าที่ผมคือ supply พวก process อย่างอื่นผมจะเป็น
อาจารย์มีคนกี่คนในทีมเหรอคะทำไมแบบทำได้ตั้งหลายโปรเจกต์
คือเด็กเรามาจากหลายสาขา เราก็เลือกโปรเจกต์ให้เหมาะกับเขา ก็คือทำหลายสาขาอันที่หนึ่งมันก็ดีคือเหมือนกับเราเห็นจิ๊กซอว์ต่างๆแล้วพอเรามีหลายๆอันเนี่ยพอเจอโจทย์นี้พวกเราก็เอาตัวไหนมาใส่คือถ้าเราทำเรื่องเดียวเนี่ยมันก็รู้อยู่แค่เรื่องเดียวพอมีโจทย์มาเรานึกไม่ออกแล้วผมต้องการดีกรีถูกไหมมันเราก็เป็นแค่เป็นพี่เลี้ยงว่าเฮ้ยแล้วอย่างนี้มีอย่างนี้อยู่แต่ว่าเราคุม
สโคปให้มันอยู่ในเกณฑ์ที่ว่า
ใช่แล้วก็เรามีอยู่หลายเรื่องเราก็รู้ว่าเฮ้ยโจทย์อย่างนี้เนี่ยจะเอาใครมาจัดการคือถ้าเรารู้เรื่องเดียวพอโจทย์นั้นมาเราทำไม่ได้
แต่มันต้องมีทีม
ก็มีก็อันนี้ก็เป็นตัวที่แบบว่าเราไม่ได้เน้นไงคือเพียงแต่เป็นเรื่องที่เราสนใจ
อันนี้น่าจะไปได้ไกลเหมือนกัน
แล้วบังเอิญที่ฟิสิกส์มชเนี่ยเขาสามารถโค้ดเทนโลกศาสตร์บนอะไรก็ได้
บนอะไรก็ได้
แล้วก็สามารถทำสเกลใหญ่ได้ทำกึ่งเชิงพาณิชย์แล้วเพราะฉะนั้นก็เราก็ใช้แลบของเขาครับ
ก็อันนี้อีกอันเป็นที่จุดเปิดเนี่ยครับเนี่ยครับแต่ว่ามันเหมือนโดนลบไปจากระบบแล้วครับได้เบอร์เมื่อกี้แบบ
แสดงว่าไม่โมโหที่โมโหมันน่าจะอยู่ที่ไอ้นั่นเขาอะก็เอาเท่าที่ได้เอาเท่าที่มีก็หามันมาแค่ไหนแค่นั้นก็เอาพันมาก่อน
ไม่แน่ใจว่ามันมีใช่หรือเปล่า
sei que tem outro. Poderia usar outro.
Tem outro, mas esse lá, esse, trocando isto.
Eu já troquei, esta
Já deu?
já essa já tentei. Esquisito, né?
Ah,
Será que foi no computador? Está bom.
já sabe dizer.
É? Funciona? Que foi que eu...
Não sei, ok. Às vezes dá-se.
Yes. Very good. So now you're cool. Now you can give your speech. I don't need to. Yes, and don't speak too long because I have no time for myself.
Yes. Nobody's here to listen to you.
I told him he should have presented his rice work.
It's actually.
Make a poster with the rice.
It's true.
Yes, everybody would have been very interested in rice. Yes, very big, very big. That's right. This wasn't from the. You're right. This was from Cali. I have the same talk in German. It's this is I took this from the Spanish version, and so this is why it's like this. This is correct. This is the problem. You need to change this. So, everybody's happy. Still works. Yeah.
No, it's.
No.
Yeah, please, right, because I think they did not finish it. Yeah, they will finish it. I tried to learn.
It's okay.
Yeah, sure. We have pictures.
You'll be here. So when it goes here,
Yeah, I will go.
this was what.
Oh, really?
She told me to wait for her and see, even though you did it.
Ah, yeah. So, oh, okay. So you just, so you got her email?
No, she came to me
Oh,
and she told me. She says info.
Yes.
So she told me. No, she told me info.
why? Oh, because it's needed. Same as professor.
Yeah, I was the one who made it.
Oh, really?
You remember?
Always come. Oh, you
but
told,
I told
you
everyone
told,
that
okay,
yes,
yeah,
people.
before. Okay, I see. Here's the way up.
So is it?
But actually, like a slide.
But we went out after. Why?
Because someone, yeah, someone really misunderstood and someone caused a lot of noise.
Who was?
But it doesn't.
And you were four in the room. And someone did a lot of her.
No.
Who? Isis?
Yeah.
Sleeping in my front. So he would come in.
But yeah, maybe you doesn't it did it perfectly. That you can speak. So that's why. But you and I think you can receive
Perfect. Yeah, but you forced from the set. My sleeping time is usually 4 minutes.
yes.
And everywhere is good.
I know.
It's very good.
In
Every
a long
time
house.
you like
Yes. I like your electricity.
Yes.
what is it you need? This is what we want.
I mean, you receive from Thai people.
So I'm saying the two is what you need and what you want.
Yeah. So, yeah.
And you think it.
Because I have to have one.
In your opinion.
Yeah, of course.
Um pouco mais do que para você.
Eu resumo. É mais chorar.
Porque
Good afternoon, ladies and gentlemen. Our keynote speaker in this afternoon is Professor Hans-Jürgen Hermann. He is head of the computational physics group at ETH Zurich, Switzerland. He received his PhD in physics in Göttingen and Cologne 1981. He became a collaborator at the Service of Physics Theory in Sacle after 1 year as postdoc in the USA. Then he became member of the French National Center of Scientific Research, or CNRS. It is the largest governmental research organization in France and the largest fundamental science agency in Europe. He was head of the many body group at the High Performance Computing Center Stuttgart of KFA Zurich for 4 years since 1990. He was a chair of the PMMH of ESPCI Paris for 6 years. In 1996, he was a full professor and director of the Institute of Computer Physics at the University of Stuttgart. He was a Guggenheim Fellow in 1986, member of the Brazilian Academy of Science, Max Planck Prize recipient in 2002, and won the Gensler Kastler Prize in 2005. He is editor-in-chief and founding editor of the Springer journal Granular Matter, International Journal of Modern Physics C, member of many editorial boards and reviewer of numerous author-reading scientific journals and many committees, including the ETH Zurich Research Commission. Okay. He has published over 600 publications in high-impact journals and more than 15 co-edited books. He has H-index higher than 70 and more than 20,000 citations. Professor, oh, my hand is a bit shaking now. Professor Hammond published, can I press here? Okay, Professor Hammond published widely in the field of physics and engineering. He is renowned in statistical physics and has expertise in modeling of flow and particle transport in granular matter, simulations of dynamic systems, lattice models like pot percolation, fiber bundle, and cloth models. He also interested in the texture of landscape and computing geological processes over thousands of years. So I shake more and more now. Thousands of years. Embedded in a complex environment. His research group is able to predict the evolution of river deltas and sand dune formation, motion of Earth and Mars. Okay, and furthermore, during tsunami disaster in 2004, if you remember, he was here. But he lived in another side of the coast. Then he survived. and actually he donated blood to people in Thailand as well for that time. Please welcome Professor Hammond.
Thank you very much for this very, very kind introduction. I thank the organizers for the big pleasure of being here again. And I apologize very much that I could not come yesterday. I had another meeting that I had to give a talk, so I only arrived today. But I hope that nevertheless I can tell you something new. So the subject of my talk is the modelization of dunes. So I will tell you how dunes function, and I will show you the first system of equations of motion of dunes, and then some applications. So dunes, as everybody knows, Well, I have here my list of collaborators. You see there's also Nuno at the end. So dunes, everybody has seen dunes before. They form typical landscapes, which are characterized, as you can see, by very sharp edges in the landscape, and we'll discuss where these edges come from, what they mean. And all the sand of the dunes comes from the sea. And this is very clearly seen here in Europe's largest dune, which is the Dune du Pilat in France, where it is about 100 meters high, and it's a huge dune, yes. So this is the largest dune in Europe. And the dunes are not just beautiful, they also cause a lot of difficulties in several places. Here you see in Brazil there's a so-called sand sheet, which is covering the land. And here you see in Egypt a dune covering a road. And this is a problem which occurs a lot. So the most modern way of solving this is to carry the sand with a truck from one side of the road to the other side. This is the state of the art. And then there are, of course, more serious problems, like this is the capital of Mauritania, Nouakchott. Here you see the airport. And there is a dune field, which is huge, arriving from Libya. It travels 2,500 kilometers. These are the houses, you see, and the people, they have from nomadic origin, so they are accustomed to take the house off and put it back again. So this is not a big problem for them, but of course for the streets and the airport, this is a real trouble. And here you see this again. And what you can recognize is that the sand spontaneously forms patterns. Now, this pattern here is a striped pattern orthogonal to the direction of the wind. And these dunes are therefore called transverse dunes. They occur when the wind always comes from the same direction and there is a lot of sand available. And finally, also here a picture from Algeria. You see fields are covered. So here we are discussing the green earth, and you see dunes that make the earth less green from this point of view. And here you see again these transverse dunes, which are orthogonal to the direction of the wind. The wind comes from here. But then you see also here another structure which forms when there is not sufficient sand. So here there's a lot of sand, here's less sand, and when there's less sand, then you have the formation of these so-called Barkhan dunes. The name of these dunes is Barkhan dunes, official name. So there exist about 100 different types of dunes that have been classified according to their shape and their origin, and most of them have either Arabic or Turkish names because of the place where they have been discovered. And we will take this shape of this, let's say, croissant shape of these dunes is not trivial, and so it's a very good guinea pig, a very good test case to look at the equations or at the results that we are discussing here. So we are going to discuss especially these kind of dunes. Of course, I could apply to other dunes, but as I said, these dunes are very characteristic, and they are good test ground for this theory. So these dunes, as you can see, they have this sharp line that I told you before. So it is this sharp line that separates two regions. This is the wind comes from the left, and so this first region here is where the sand is transported by the wind. It is moved upwards and has a slope of about 10 degrees, 11 degrees. And behind this sharp line, this other region, which is called the slip phase, is much steeper. It's about 35 degrees steep. And there, the sand moves because of gravity. It means it slides down in form of avalanches. So these lines, these edges, they separate two types of regions. One of Aeolian transport, Aeolian comes from wind, and the other one of gravitational transport. So this is the meaning of these lines. Yeah? Okay, and these Barkhans exist in huge fields on Earth, typically along corridors, along the ocean, along the coast. This is a famous field in Peru in which they have been studied first, but they also exist on Mars. Here on Mars, you also have dunes, and they also exist Barkhans. And come back to Mars in my talk, and at the end of my talk. So when I start talking about Mars, then you have to wake up again. So far now, the introduction, and now we'll have a little, because unfortunately I am a theoretical physicist, and I'm supposed here to tell you about the theory of how dunes move and equations, so I must a little bit become technical, so I hope this is not too terrible. So, this is a schematic view of the dune. Here you have this edge, this is a slip face, and the first thing one has to realize is that the dunes are aerodynamic instabilities. That means the dune cannot be separated from the behavior of the wind. You have to understand the wind if you want to understand the dune. And so you can check this experimentally very easily with smoke. So if you release smoke from a place, then you can see from this how the wind is moving. And what is interesting is when you release smoke from this edge, from this called the brink, or the crest, from this sharp edge, what you see is there's a separation of flow. There's a part of the air which goes like circular motion here, and another part which goes on top. And when you consider now that the wind carries the grains of sand, then what happens is when these grains go in this region, they fall here down on the ground and cannot move again because the wind goes in the opposite direction. And it's actually much weaker. I have some picture here. So here this is a simulation using a CFD code of such a shape. And what you see is, this is the scale of velocities. You see that the velocities in this region here, which is also called the separation bubble, is much lower than above. So the strength of the wind is not sufficient to carry the grains. So what happens is that the dune, technically speaking, is a trap for sand, which is made of sand. So the sand constructs its own trap. And that is the whole, let's say, physics, if you want, hand-waving physics of the dunes. And in principle, you have understood what goes on. But of course, what I want to do is to calculate these shapes. And for that, I have to go a little more deep into the, let's say, mathematics. So the first thing one has to understand is that the wind is turbulent. And so this makes it very hard to solve numerically. And in particular, there's one very important law that was discovered already in 1924 by Prandtl, that in the turbulent flow, the velocity of the wind increases with height logarithmically. So on the ground, the velocity of the wind is zero. It's equal to the velocity of the ground. And the higher you go, the higher is the velocity. And the law is this one, where z is the height. And since the velocity is not constant, if you want to characterize the wind strength, you either have to define a certain height at which you measure the wind, or what you can do also, and what is done in this field, is one characterizes the wind strength by the prefactor in front of the logarithm. This is a very elegant way, and so I will use this as the measure of the strength of the wind. And this is called U star. And in fact, it can be shown that this U star is proportional to the square root of the shear force that the wind exerts on the ground. So the wind, of course, has a gradient in velocity, and this exerts a certain shear force. And this shear force is, of course, responsible for the transport of the sand grains. So there is, of course, a lot of work has been done in the past, and there exists a group in Cambridge of mathematicians which in the 70s was able to reduce the three-dimensional velocity field of the wind to a two-dimensional problem. Namely, they were able to, let's say, integrate the profile down and obtain a formula for the shear force exerted on the ground as function of the shape of the landscape. And so what I will do now is I will introduce three different fields to describe the problem. One is the profile of the landscape, which I call h. Small h, yes, small h of x is just describing the topography. And then the second field I will introduce is tau, which describes the strength, the shear force that the wind exerts on the ground. And finally, I will introduce a third field, which is the flux of sand on the surface. And the aim of the next 10 minutes, which will be the toughest minutes of my talk, is to show you a set of 3 coupled equations, complicated equations, for these 3 fields. And you know, if you have 3 equations and 3 fields, 3 unknown fields, with 3 equations and the corresponding boundary and initial conditions, then you can solve the problem. So that is the aim. So what these people in Cambridge were able to show is that, this is the simple way of showing it actually, is how now the shear force on the ground depends on the height of the landscape. And what you see, this formula looks very complicated. It is complicated because the hydrodynamic field of the wind, of course, is a long-range field. So it depends on very far distance of the landscape. So you can imagine if you come from a valley, far away from a valley, you have more strength than you come from a mountain range. And so therefore one has to integrate over the entire field in order to calculate this strength. So there actually are 2 terms. This is this non-local term for the non-local hydrodynamic effect of the wind. And this here is a very simple local term which just says that the more steep the landscape, the more the wind is deflected and the stronger is therefore the shear force exerted. So this is a formula which you have to just swallow, like you swallow the food at lunch. And there come more of these formulas, but I'm sorry, this is like it is. So this is like a formula which is known since the 70s. The second thing we have to discuss is how do the grains move? How does this shear force produce a sand flow? And the pioneer of this whole field is this British brigadier from World War I. From World War II. He fought with Montgomery in the desert against Rommel. And he was an engineer by education. So during these 3 years that he was in northern Africa, he made a lot of small field experiments. When he came back, he wrote the most famous book on this field, the pioneering book, in which he explained essentially what goes on. And he discovered that the mechanism of transport of the grains, of sand grains, is what is called siltation. In fact, there exist 3 different types of mechanisms in the wind: creep, siltation, and suspension, depending on the size of the grains. If the grains are very big, like larger than 300 micron in diameter, then the wind is not strong enough to levitate them, and then they will stay on the ground. But they move, so they have creep. They move slowly on the ground. So this is not a very important effect because it's a very slow motion. So this is not an effect which will produce dunes. Then if the grains are too small, they are smaller than 50 microns in diameter, then they are so light that the wind can carry them very far. And sometimes in Zurich, we have on our drying clothes, we see some reddish dust which comes from Sahara. So this goes over the ocean. Yeah? So this is, of course, also not relevant for dunes because the sand is gone. So the grains that form dunes are between 100 and 300 microns, and they move according to this mechanism, which is called siltation, and which means that the grains jump, because saltare means jump in Latin. So what happens is that for some turbulent eddy, whatever, one grain goes up. I show you, okay, and it goes up. The higher it comes, by chance, it's just moved up, let's say. The higher it goes, the stronger is the wind, because the wind increases with height, and so this grain will be accelerated by the wind and gains a lot of energy. But then, of course, after some time, it will fall down because of gravity, but now with a lot of velocity, it will impact on the ground. And this impact will produce a splash of new grains, which then again will make these trajectories and again eventually an exponential increase in the number of grains. But of course nothing goes forever. Can anybody tell me what is the limiting factor? Why does this not grow exponentially all the time? Which law is this? There's a law in mechanics which limits this growth. It's a conservation of momentum. Yeah, because each time the wind accelerates a grain, the wind also has to lose momentum. And so the wind is weakened by the carrying of the grains, and there is a point in which the wind cannot carry more grain because it just all its momentum is gone, if you want. And this is then the limitation of this growth. And this flux that you get there is called the saturated flux. You get a saturation of this exponential growth. Okay, I show you now how this looks like. So this is a movie from Brazil. And here you can see this citation mechanism. You see, it's very difficult to see maybe because it's here on a white ground. So I show you maybe a movie on a dark ground. So here you see better what happens. So the citation, when you have probably seen it all when you have ever been on the beach on a windy day, it seems as if the sand is floating over the ground at something like 5 or 10 centimeter height. And then you have, of course, this kind of a random motion due to turbulent fluctuations. So this is the citation mechanism. Well, let me go a little bit more in depth. This mechanism, of course, can be studied in wind channels very carefully. And then people have established a certain number of empirical relations for this saturated flux as function of the wind strength. So for instance, this is the simplest law established by Bagnold already, which is only valid for very large wind strengths, which is that the saturated flux grows like the cube of the wind strength U star. But this is too simple. It has been seen as incorrect. In fact, what one discovers is that there exists a threshold below which there is no flux. And so this is another law which was formulated by Lettau and Lettau, which describes the flux better, and there exist about 15 such empirical relations. So the first thing one can ask is, can we obtain these relations also by other means than just measuring in the wind tunnel? And what you can do, of course, is you can numerically simulate a wind tunnel. So here I show you this is a numerical wind tunnel in which we have now imposed from the beginning this logarithmic velocity profile, which we know exists in the turbulent flow. And here you see now, this is this numerical wind tunnel. One imposes a certain type of trajectory of a certain height and a certain length and a certain mass. And then you can see that either, if the wind is too strong, these trajectories will start to increase, get higher and higher. And when the wind is too weak, the trajectories will go down. And there will be exactly one velocity or one mass of the trajectories at which one has a stationary situation in which all the jumps are equally high. And that is then the saturated flux. And here I show you now the final result. This is now the wind strength here, and this is the saturated flux, and that is what you obtain. Here we have this threshold below which there is no flux. And then what you find is that here in the beginning, the flux increases like a parabola, and later, for large velocities, as we know, it increases like U star cube. One can go further, and one can do a simulation also in more detail. So one can do, this is very expensive actually to do, in 3 dimensions. This is a simulation in which you now impose again this logarithmic profile, and now you simulate the force that is acting on grains by something which is called discrete element method or molecular dynamics. And then you see that, of course, you do not have just trajectories of equal height. This looks much more complicated. You have some particles on the ground, some particles very high. So one can also study this in more detail. And actually, the simulation allows you to study exactly the impact, the splash. Simulate the splash. And what you see is that there are particles which, like the green ones, which are moving, but not very much. So this is a kind of creep. And then there are others which are ejected and fly very high. And what one finds, it's interesting just as a remark, is there exists some kind of particles which are called saltons, these are the yellow ones, which nearly never touch the ground because they jump on top of other particles. And these yellow particles essentially are always very high, and so they get a lot of energy from the wind and are very fast, and those are the ones that contribute most to the flux. So if you look at the flux as function of velocity, you can decompose now into the three colors I showed you before, the yellow, the red, and the green, and you see that these saltons, which are very few particles, but which make huge jumps and nearly never touch the ground, they contribute mostly to this flux. Okay, so doing this numerical calculation, one finds that actually at the threshold there is a certain jump in the flux. This is also something, and one sees that depending on the velocity of the wind, one finds the loss of momentum of the wind at a certain height to be highest. So you see, this is for weak winds, this is for strong winds. What you see is that there is a certain height at which the wind loses most of its momentum. And this is exactly the height that you have seen in the movie, at which it seems that the sand is floating on the ground. And one can study now how this height depends on the wind strength, and one discovers that it goes linearly. Okay, so far to the mechanism of saltation. And now one has to write everything down in equations. And sorry, now comes the next equation. This I will not explain too much in detail, but one can now describe how the flux changes in time and space. And one finds that if this is the expression for the saturated flux, then there is an evolution of the flux such that when Q equals the saturated flux, then the change of flux is zero. So you have an increase that looks like this. The flux increases, as I said, exponentially, and finally it saturates. So this that you see here is just a result of these equations. So this equation is another of the equations I'm going to use. So we already have one equation which describes what is the shear force as function of the height, and here now you have an equation that describes how the flux depends on this shear force, because all these quantities, the saturated flux and the lengths here that you see here, depend on U star. So I don't want to go too much into details of the equation. Just I tell you, one can have an equation now for how the flux behaves as function of the shear force. And finally, one also needs to close this with a third equation, which is nothing but the mass conservation. It means, of course, the flux will move mass, and this movement of mass is going to change the height of the landscape. And this is this equation here. So at the end, one has these three equations. I showed this before, then I showed this logistic, and like this. You have three equations, you have three unknown, and then you can, with this, solve the system. So this is the hard part. And there's one more detail one has to say, which is that dry sand can never be more steep than a certain angle. And this angle is called the angle of repose, and it corresponds actually to the angle of the slip phase. The sand becomes unstable when you go beyond this angle, and then the sand starts to slide down. These are the avalanches. And so one has to additionally impose another condition, namely that the slope of the landscape must always be smaller than the angle of repose of the random material. And this condition is imposed a posteriori. Once you have calculated this, one has to actually construct this, and these conditions finally make these sharp edges that you have seen in the beginning. Okay, so these equations can be solved. Okay, this is another detail. I will not discuss this. You can solve these equations in this iterative way, and that's it. I don't tell you more than that. You need a certain number of smart students because you have to calculate this integral, and this is done by Fourier transformation. So let's not be technical. Let's just say we have solved these equations. And now let's see what happens. So first of all, one can play around and see how does the system behave. One can, for instance, start with a small hill, yes, with a certain mass, and then put the wind and see how this hill evolves. And so here I have two hills, the blue one and the red one. Both hills have the same volume. And now I let them evolve. This is here the height of the blue one, the height of the red one. So the red one gets higher, the blue one gets smaller, and after some time, both converge to exactly the same dune, which looks like this here you have the slip phase, here you have this edge. So you get a dune. And interestingly, it is independent on the initial condition. Then you can also change the height of this hill. And then you can see that if the hill is, or the size of the hill, the volume of the hill, if the hill is too small, then the final result is not a real dune, it's just flat, which is known. One knows from the field that there are dunes of less than 1 meter height do not exist or are not stable because the wind blows them away again. So, in fact, only from a certain height on, one obtains the slip phase. And this is somehow also understandable because you remember the slip phase was a place in which there was this shadow in which the particles fell in. And if the dune is too small, then the sand will not fall in, it will just jump over the hill. And therefore there exists this minimum size for a dune. And this is reproduced by the equations. So, in order to be, of course, serious, because this is all for the time being just a theory, one has to verify these equations by comparing them to the experiment. And unfortunately, dunes are very big. As I said, the smallest height is 1 meter, which represents 40 meters in width and 60 meters in length. And then there exist, of course, much higher dunes. And so laboratory experiments are very difficult or impossible. And so one has to go to the field. But of course, on the field, one has a less controlled situation because you don't know the full story of the dune. And so it's a little complicated, but anyway, we went to different fields and checked a little bit our equations. So this is in Brazil, in the northeast, a field which lives between, it's on a peninsula. So the sand comes from the ocean, as I told you before, and moves over this peninsula, and then the dunes fall back into the sea. And when you take pictures from different times, here there's 30 years difference, and you superimpose them, then you can see how much every single dune has moved. And here you see, for instance, this is the highest dune of the field. It moved 263 meters in 30 years, which is on average something like 8 meters a year, which is, for such a huge dune, very fast, because the winds are very strong. In fact, the velocity of the dune is inversely proportional to its height. This is because the flux is a surface flux. It used to transport the entire mass. Okay, now we went to this field, and here you see the dune. This is a huge object. This is more than 1 kilometer long. And on this map, we looked at large dunes because there you have, of course, higher precision in the data. And we measured on the dune now the wind strength and the flux. And the flux, the sand flux, can be measured in a very simple way. Namely, you take a hollow cylinder which has 2 slits, in front and in back. And on the back slit, you put a small grid which does not let the sand grains pass. So the wind that carries the sand goes inside this tube, and then the wind can go through, but the sand grains fall into this hole. And so what you do is you just put this in the field, and then you wait a certain time, then you take it out and measure how much volume you have inside, and then you know how much sand has been carried during that time. Okay, this is a little simple. In fact, what we have done also, we have simulated this object and studied exactly how much sand enters into the, because it's of course a hydrodynamic object. And so what we did is we measured the velocity and the flux along a certain line over this dune that I just showed you. And here you see now the results that we measured. The continuous line, no, the data point are the experimental measurements. This is the shape of the dune. You see, this is the edge, this is the slip phase. And the continuous line are the result from the calculation, from the equations. And you see there is a very good agreement. This is now concerning the wind velocity. So you see there is a dip in front of the dune and the velocity, and then it goes up. So we get quantitative agreement concerning the wind velocity. And we also get quantitative agreement concerning the sand flux. Where I have the measured curve is the black one, and this dotted one here is a curve in which we have neglected a certain term, just to show that you cannot even neglect this term. So, but you see the agreement is very well, very good. The second test we did was in the desert of Morocco. In fact, it was not exactly Morocco, it was a piece of land that Morocco has taken from Spain, in which there are phosphate mines. And these phosphate mines are transported to the sea. So here you see the mines are somewhere here, and there's a conveyor belt that carries this phosphate to the port where it is shipped. And this conveyor belt goes through this gray zone, which is in fact a huge Barkhan field of about 200 kilometers long and 20 kilometers wide. And this has been, since 40 years, an engineering challenge to have the conveyor belt go through this dune field, because all the time the dunes cover the belt, and you have to clean the belt, you have to move the dunes. The Spanish, they put the belt up, they make the pillars and have the belt 10 meters high. What happens, the dunes get stuck at the pillars, grow up, and again fall on top. So everybody laughed about the Spanish engineers. So the problem is not really solved yet. Anyway, this field is very interesting to be studied, because you have here a large variety of dune sizes. So one can understand how the Barkhan dunes depend on their size. So here you see, this is how it looks like when you go there. Actually, it was quite dangerous, because there's this Polisario that put mines, and you had to go with the military not to get the minefield, so it was a little fun. Anyway, what you see here now is that the length and the height of the dunes are proportional to each other. So the dunes have a certain shape, which is scale invariant. And these are the experimental data here, and these are the numerical data. And what you can see is the slope of this line depends on the wind velocity. And in fact, what one can do by doing the simulations is to extrapolate which has been the average wind velocity over the field for a certain number of years. But one can go much further. One can also compare the entire shape of the dunes. So here, this is a longitudinal cut through 8 different Barkhan dunes. This is a numerical and experimental. And what you see is, of course, here the slip phase, and here the edge. But what we have done is we have rescaled all the dunes such that they have the same, they fall on top of each other. So, in fact, this dune here is much larger than this dune there. What one finds is that, in fact, one can distinguish large dunes from small dunes, because in small dunes, the edge, this brink, is at the beginning, in the very beginning, and the more the dune becomes larger, the more this parabolically shaped edge moves backward. Anyway, this is why when the larger dunes, they have the line shifting to the right. And now what you can see, actually, what we compared in detail, is that you really have quantitative agreement between experiment and simulation. But of course, the simulation is much more clean. You see, they collapse. The shape of the dune on the right-hand side is the same for all the dunes, yes? And this you don't see so well here, because on the field there's a lot more fluctuations, and you don't know what the past was. So these are experimental problems, which have, the numerical problem doesn't have this. I should say something, it's very important, is that the calculations are more than 10,000 times faster than the reality. Which means, we can simulate, which means that one can, this is what I'll show you later, one can predict or explain things which one can otherwise not observe on the field. Okay, what we find for the longitudinal profile, we also find for the transverse profile. So the wind comes from here, you can cut the dune, and then you see here 8 experimental dunes scaled on top of each other compared to 8 numerical dunes, and you see both of them follow very nicely the parabolic shape. Okay, so after all this, we are now confident that this program reproduces quantitatively the dunes. And now we can start to play. So the first thing we can do is just to see how does such a field look like. So we place small mountains, Gaussian shape, on the plane, and then we put wind from here, and what happens is that you form automatically Barkhan dunes. Yes? Some of them disappear because they get too small, a bit larger, but you from these dunes. Now, the next question is, how does this actually appear? I mean, yeah, here I started with these hills, but normally there are no hills. So now we do another experiment. We start from a beach. We take an infinite beach, or a flat beach, perfectly flat beach, and we put wind coming from the sea. And what happens? So this is my beach. The wind comes from here. You have to look very carefully. You see, and suddenly you see these lines. You see this, and suddenly these lines decompose. So what you can find is that the system has two instabilities. First of all, the perfectly flat beach decomposes into transverse dunes. This is what transverse dunes, I told you what it is. And these transverse dunes happen to be unstable, and then they decompose into barcans. And so you get these barcan fields. So this is experiments done underwater. You can, for certain conditions, you can compare with water experiments, and you see on the water you have the same instability. Actually, you can, this I will not discuss, but you can actually make a stability analysis. And you can show that this instability does exist. Okay, so now we understand the formation of these dune fields from nothing. I mean, the genesis really from the plain beach. Another interesting question is the collision between dunes. As I told you, smaller dunes are faster than large dunes because the velocity is inversely proportional to the height. So what happens if you have here a large dune, and behind the large dune we have a small dune, and now we put the wind coming from the top down like this, so these dunes are moving, and this dune here will catch up with that dune. What happens? Well, they're moving, this moves towards that one. We are in the moving frame, so they are moving, yes? So this dune is in the shadow of that one, and since it's in the shadow of this one, there's sand which is staying behind because the wind is not strong enough, and so the small one behind is going to eat the sand that the large one leaves behind. And after some time, the dune in the back, which was smaller, becomes bigger. And then the moment when it becomes bigger, it becomes slower. And so, at the end, this is the smaller one, it's the faster one, it can escape again. You see it now, it escapes, it goes away. So this happens when the two dunes are not too different in size. They are different, but not too much. So one has this situation, it starts with the smaller back, and at the end it's the smaller front. So one has the feeling that they do cross each other. They do not, but it's the feeling they do cross each other. And in fact, this is a behavior which is called solitary behavior, solitons. There's solitons, and one can actually show that there's a relation to the Kadomtsev-Yashvili equation, which has this kind of behavior solutions to. But let's not discuss that. So another issue one can discuss, what happens if the dune is much smaller. If it's much smaller, then it comes with a higher velocity, and it's not able to really do the process I showed you before. With a collision between the dunes, they coalesce. But as it often happens, when two coalesce, they produce babies. As you see, there are no babies. Each horn produces one baby. Well, this is an effect. But what is interesting is that this effect solves a very old problem, which is a problem from China, or from Gobi, which is this situation here. This is a very famous riddle from geography. Namely, one has these so-called mega dunes, which are so big that they nearly don't move anymore. And one has discovered in front of these mega dunes, small dunes. And nobody understood how can these small dunes appear in front of the large dunes. Since the small dunes are so fast, they should have gone away since a long time. But they are there. And the reason is the one I showed you. What happens is that once in a while, there's a small dune coming from the back, and pop, pop, come out the babies. This is the explanation for this. But nobody has understood this because nobody was able to do the calculation over the time that it takes. Because this procedure, in reality, takes hundreds of years. But on the computer, it takes only a few days. Okay, so that's the collision of dunes. The next interesting issue to ask, this is now, we are here in this green conference, is the question of vegetation. And the vegetation has two roles. On one hand, the vegetation is able to fixate the sand. It puts roots and the sand cannot move anymore. But on the other hand, especially when the wind is very strong, the sand can have something like this. And there's always this play between the two, vegetation and sand, and vegetation and sand. And so this can be actually explained. And one can now add to the equations that I showed you another equation describing the vegetation. Namely, I introduce a new variable which I call HV. So this HV is not the same as H. HV is now not the height of the landscape, but the height of the vegetation. And the higher the vegetation, the more the sand motion is hindered. Yes? But on the other hand, the faster the landscape changes its height, the more the vegetation is destroyed. So either you kill the plants by covering them with sand, or you kill the plants by removing the sand from the roots. You can destroy them either by increasing or by decreasing the level of the landscape. And so we have now the following equations. The change of the vegetation is given by a growth rule. It grows with velocity tau up to a certain height. But then it's a minus the change of the height of the landscape. So this is the construction factor, the growth of the vegetation, and this is the destruction of the vegetation due to the sand. And this is the equation for the vegetation, and then this couples to the transport of sand here, so that the shear force that we discussed before of the wind will now be reduced if there is a certain vegetation in such a way. This equation here is an empirical equation that has been obtained by measurements by this guy Aupach in the field. So you can make fields and then you can study. This is very important, of course, for fixation of dunes. We have to study how is the effect of the vegetation on the erosion of the ground by the wind. And if you do this now, you can couple this equation to the other equations, and again you get a smart student has to solve these equations. And what you find is that the dunes evolve. So for instance, here we have a Balkan dune in the dry period. There's no vegetation. Now starts the humid period. It starts to rain, and the vegetation starts to grow. It grows everywhere, except where the moving of the sand is too strong. Here, there's a lot of sand moving, so it cannot really grow. But the vegetation is growing and growing, so what it does is it fixates the lower part, which are left behind, and only the front part moves until everything is fixated. And so what you do is you transform this Balkan dune into another shape, which is called a parabolic dune. And this procedure here, that happens here, happens all the time along the coasts everywhere, in particular on the Brazilian coast also. So you can see, if you look in Google Maps, if you look carefully along the coast, you will see lots of these so-called fossil dunes or fixated dunes that have this shape. And then here I just show you some images I've taken from Google comparing this kind of evolution. Of course, nobody has ever seen the full evolution, because the evolution from here to here takes another, let's say, 100 years or so. Yeah? So this, of course, the shape of this final parabola or for these final dunes depends on the ratio between the growth of the vegetation and the velocity of the wind. And so this ratio here now can be changed. And that's what I show you here. So these are now final parabolic dunes, final fossil dunes, yes, for different vegetation speeds. So this is when the vegetation grows slowly, or little vegetation, then the dune is fixated rather soon, while this is when the vegetation grows slowly, here it grows fast, the vegetation grows fast, and the wind is slow. And here, the vegetation grows slow, and the wind is fast. And so the dune is able to move further. But at some point, they have to stop. And here you see then, again, comparing images from Google. So, and now, happy, we come to Mars. It's ending. So Mars is one of the many planets that do have dunes. And these dunes form fields, enormous fields. Here I show you, for instance, these Balkan fields. You might notice that these Balkans are not identical to the Balkans I showed you before. Yeah? They have a much smaller mouth. It's why I call them cockroaches, not Balkans. And in general, the dunes on Mars are not like the dunes on Earth. And so it's an interesting challenge to see if this equation is able also reproduce the dune of Mars. And so what we have then done is to look at all the parameters that enter into the equations. And there are a total of 10 parameters that enter the equations, but all these 10 parameters, except one, can be directly obtained from the literature, like the gravity of the planet, the density of the atmosphere, the density of the grains, the diameter of the grains, and so on. These things are all known. So you can replace the numbers from Earth by the numbers from Mars. Except for one parameter, which is related to citation, which is a parameter that tells you how many grains are produced by the splash, by the impact. Remember, there are several grains. And this is something which you can obtain by simulations, but it is not clear how the grains, how high they can jump, let's say, on Mars. And so we don't know this parameter, and so my student said, well, I don't know what to take, and I said, let's take the same value as on Earth. Why not? Let's try. And then, this is the parameter. What he did is he put all the numbers of Earth into the numbers of Mars, and then he took gamma equal from the Earth. And what he found was nothing. Nothing, yeah. But then when he changed gamma, at some point when gamma was 40 times the Earth, he obtained exactly the cockroaches. And this can be done also for other shapes of dunes. So what you discover is, indirectly, by this technique, what is the citation mechanism on Mars? And you get the gamma on Mars. So here you see the comparison, again, for the dunes on Mars and the simulations of the dunes on Mars, as compared here to the dunes on Earth and the simulation of dunes on Earth. So you see clearly that these dunes have different shape. And as I said, there exist many other shapes on Mars that we have never seen on Earth. Like these ones, these for instance, these dunes have not been classified in the classical time, so they don't have an Arabic name, they don't have a Turkish name, so they are called fortune cookie dunes. And this is their name now, given by NASA. And these are all these dunes have not seen. These are images from the mission. These are Mars dunes, and these are numerical dunes we obtain using the program. So these are dunes actually which you obtain when the wind changes its direction periodically with an angle of about 90 degrees, and you get these fortune cookie dunes. So summarizing, yes, one is able to even explain dunes in different conditions, and of course the challenges don't stop. This is dunes on Titan, for instance, longitudinal dunes, and also these dunes can be studied, etc. So I close here by a small outlook. So first of all, as I said, there are hundreds types of morphologies, so there's a lot of work still to be done to understand all these morphologies. Then it's interesting we have of course also many applications for this. We've worked with coastal management in Holland. We've worked on desert and fixation of desert dunes with Mauritania. And always there, the problem is, of course, what is the wind strength in this region? So one couples the meteorology to the program, and then one can get a long time prediction of what happens. Then another thing which also we are involved in doing is to probe measures of protection and measures of fixation of dunes, because here the big problem is that also people don't know what happens in 20 years. So people make, for instance, there's a big famous street which connects Timbuktu and Nouakchott, which is called La Route de l'Espoir, which goes through several dune fields, and the UNESCO has, the United Nations have made a program for who is able to stop the dunes on segments of this road. And so people, companies or people have made some techniques, destruction of dunes or fixation with plants, whatever, but nobody can say what happens in 20 years. And so this is very important to do it numerically. Finally, there exist also dunes underwater, like the Bay of San Francisco has huge dunes, for instance, huge dune field. And finally, what I did for vegetation was very simple. I took just one type of vegetation, which is of course very simple. In reality, there exists grass, but there exist also trees, and they have a very different effect. So there's a lot of things to be done. So thank you very much.
It was very excited talk. Yeah. Please, question.
you for your talk. I like it a lot because I know now that when the sand's coming up to be the dune, and after that when the wind comes, it's going to change the shape. Like you said, it's catch up the small one and the big one. But I wonder whether this kind of in Sahara is follow this kind of pattern also. All kind of dune will be the same.
Yes, this is universal. Every desert, every dune follows the same equation. Yes.
And so it's going to be like a big barrier in Sahara. It's going to change the shape a lot according to the time, right? And you can predict in the future what it will be the shape.
Yes, you can calculate, even knowing how the situation is today, and knowing how the winds are on average in the region, you can predict what happens 10,000 years later.
How about tornado or some kind of effects of the wind change, like the lower pressure or high pressure of the air will affect this kind of?
The pressure of the pressure, what you call pressure, what you measure with a barometer, does not influence the dunes.
How about
it's the velocity of the wind? The only thing is strong. The only force that is important is the velocity.
Velocity of the wind.
Of the wind.
How about water effect?
Humidity.
Yes.
This is an important effect. Yes. So everything I discussed was for dry sand.
Yes.
When it rains, then the sand cannot move because the sand is fixed, because it's cohesive. The water makes an attraction between the grains. You know this. You can build castles of wet sand. So wet sand is like a solid. Okay. Now, of course, the sand dries very rapidly in the sun. So what happens very often is that the upper layer, even if the sand is wet, the upper layer dries, and then these grains are moved.
So the top is going to move, but the bottom still be there, right?
Exactly. So what is interesting, I have some pictures, I have to search them, is that there are regions in which there is the groundwater level goes in the middle between the dunes. I mean, there are some dunes which look out and some dunes which are below. So this this level of water will decide how the dunes look like. So this is another parameter. We've done even a full PhD thesis on the issue, how the interaction is of this level of the water, because of course, then there are regions in which the dunes can move, but then when it's below the level, then the sand is again stays there.
So you mean that this prediction may have some other factors that have to think about it, depend on the area, that one?
Yeah, well, the water and the rain is very important. This is one of the facts which are crucial.
In Thailand, we don't have much sand, so we consider that one not a big problem, but it's good though.
This is maybe not very relevant for Thailand.
Yeah, but it's good.
I have a question about the distribution of the size of the grains. I think the size mixture is not always the same. So I mean the small particles and larger, medium size and so on. And is there an influence if you have a different distribution of the sizes of the grains?
Well, the measured sizes distributions in the typical desert are Gaussian distributions that are between 100 and 300 microns in size. Because this is a mechanism that is relevant, the siltation mechanism. And what one finds is that the small particles, the fine particles, go to the top of the dune, while the large ones stay on the bottom. This is opposite to the so-called ripples. Everybody has seen ripples, which are these patterns that you see also in the sea, that are like lines which have a distance of about 10 centimeters. And these ripples, they have the opposite. The large ones are on top, and the small ones are on the bottom. So you can distinguish between dunes and ripples.
So can I ask one question? So have you simulated like tornado or things like tornado like this spinning wind? Like, no. So I wonder the pattern or the sand formation for the tornado like spinning wind. So
In this technique, I cannot simulate this technique because, as I showed you, I have integrated down the three-dimensional flow field to some two dimensions, so all these structures are lost. But also these tornadoes are actually a rare event, not common. But what is more common are the temporal fluctuations of turbulence. And they actually, we include them, I mean, I didn't talk about this, but there exists a very, very powerful way of doing this that was invented by somebody called Reynolds, but not the Reynolds from Palmer, new Reynolds, 2003, in which you can add what is called stochastic forces, but that follow all the statistics of turbulence, convergence, scaling, everything. And you can do that, and then you get on top of what I've shown you, because everything I showed you was the stationary velocity of the turbulent field. Yes? But if you add these fluctuations, then you can get additional, let's say, sand flux. It means the threshold that I showed you moves down. Everything stays more or less the same, but the threshold moves down. Very good.
One stupid question.
No,
The wind come just one way or usually come to many ways? I wonder when one time it's come to this way and later in the afternoon possible it come this way and that way, and this kind of do will be the same shape like this?
This is a very, very good question. Actually, there exists no stupid question, there exist only stupid answers. So, let me say like this. So this question is excellent because this is actually what makes the different shapes. So the shapes I showed you, the transverse dunes, the Barkhan dunes, are what happens when the wind comes always in the same direction. If the wind changes direction, you get different shapes. Whereas if the wind changes by 45 degrees, you get what is called scythe dunes, which are longitudinal, which are lines along the wind. Yes. And if you have the wind rotating, then you get what is called star dunes, which are static dunes but have like spiral arms, and so on. So exactly what is a very good question. This is one of the fields where a lot of work has to be done, is what happens in different scenarios when the wind changes direction.
Have you studied methods to contain dunes?
Oh yes, yes.
What's the most effective?
Well, on short time scales, the most effective is to use the wind to destroy the dunes. There's a guy called Meunier, he was a French coopérant, who studied this carefully. You put in palisades, small walls of height of 30 centimeters, and place them in very strategic way on the field, and they form channels of wind, and this wind channel digs its way through the dune and separates the dune into small pieces. This is on the short time scale. On the long time scale, you have to plant, you have to put trees. Yes? So what people do is they go stepwise. First they destroy the big dunes, then they put some kind of a textile on the floor just to stop it, and in the textile they plant some plants, some plants, and then they wait for this to go.
But how many particles that you simulate?
The simulation of particles, this was of course a small system, is about 2,000 particles only. Because this is very expensive. You have to wind, you have to calculate the wind, you have to calculate the drag force, and so on.
And then you can predict for
No. The simulation of the equations are continuum equations.
Okay.
I don't describe the individual rates. See, they were just differential or integral differential equations. Complicated, but that's where it's continuum. Yeah. When I showed you this simulation with particles, this was just to obtain the relation between the flux and the strength of the wind, which I later insert into the continuum equation.
Okay. So some other questions? Okay. Yeah. Thank you very much for your talk, and yeah. So we will move on. Next step. Yes. So this Vice President will.
Stand in the middle.
Thank you very much.
Thank you very much for coming.
Perché? No, è perché Marte a Vitória são muito mais altos. São 100 metros. Muito.
Maybe Oklahoma disagree with you about this. Tornadoes in the world.
You were countryside. Oklahoma.
Changes. Respectfully disagree with you on this point.
So if you check, yeah.
Não, mas é só a trajetória, não.
Sim,
Em princípio é possível calcular isso com as simulações do Marte.
Não.
Não?
Não, porque você precisa de sistemas muito altos.
Uhum.
Quer dizer, simular Marte é tanto para numericamente como no canal de vento hoje não é possível.
Mas não seria. Não há também um efeito do tamanho das partículas no gama? Da distribuição do tamanho dos grãos? Não pode afetar o gama?
Também entra. Quer dizer, os grãos de Marte
Podem ser mais pequenos.
Não, são maiores. Não, claro, porque, veja bem, eles vão 100 metros na Terra, eles só a saltação é 10 centímetros. Ali é 100 metros.
100 metros.
E logo os grãos são maiores. Então, obviamente, eles impactam.
Eu achei o valor impressionante, porque se fosse só uma coisa de gravidade, não é? Eu esperaria um efeito de 3, 4 vezes maior, não é? Que uma gravidade. Mas de facto.
Mas também tem que ver com o fato que a resistência do ar é muito menor. Porque se é muito diferente a densidade da cápsula. Bom, agora o que tem lá dentro? Ok, agora vamos dormir.
Exato, possivelmente a pessoa que não dormiu nada. Não, vamos ver se eles têm lá um formulário para a gente assinar, se uma vez depois desaparece e nunca mais recebemos.
This side here.
Já